Oh, that's okay now? Okay. Yeah, so I started working with Qt back in version 4.2. I fell in love with it, and I've been using it ever since. My previous work placement involved working for Lassie, where I did a lot of Qt-related work. Amazon, where I did none, so I didn't stay. And now, more recently, I've been working as a senior software architect at Devialet. Yeah. So the agenda of this presentation, I'm going to do a quick presentation of the company. It's not a well-known company, but it's coming up. I'll talk more in details of the Devialet Phantom, the product we made with Qt. We'll see how Qt was instrumental in making this product, and we'll see some of the best practices which allowed us to make the product pretty quickly, within a year of time. So first of all, Devialet. So Devialet is a French company which was founded in 2007. It was created around a major innovation in audio amplification technologies called ADH for the hybridization of digital and analog amplification. Analog is really good for being really accurate in reproducing the sound, and digital amplification is really good at delivering power, but at the price of quality. So by making a hybrid of the two, we managed to have a very compact, efficient technology which allowed us to get a really high power in a very small package, basically. The company is really, so coming from that, the company has been a hardware company where software is something of mystical, so it has its importance for the rest of the talk. So we're based in the 2nd district of Paris, and our ambition is to become a global leader in the audio technologies. So our very first product was this, the Des Premiers. It looks like something you can step on to get your weight, but really it's not. It's an amplifier, which was basically the demonstrator for this technology I talked to you about. It won a lot of international prizes for its audio quality, and it was really a way for Devialet to set itself as a major provider of audio technologies. So in terms of software, it was really limited. We had a very basic Wi-Fi streaming, which is really raw audio streaming. It's really an embedded platform in terms of it's only firmware running on microcontrollers, DSPs, and FPGAs. And we still managed to get an upgradable platform with an SD card-based update. So this platform evolved over the course of 3 years, to become the expert range. Basically, it's almost the same design, except that we managed to deploy the technology in various ways to create a range of products rather than a single product, and make sure that we had an offering at different price points and different power outputs. So basically, the names of the products are really just their pure output wattage, 120, 200, 400, and 1000. On this version, we added Ethernet connectivity because Wi-Fi can be really unreliable in some urban areas. And it still held no operating system. So this took us from this design of classic audio amplifiers to something completely new for the company, which is the Devialet Phantom. So Phantom, it's our first truly connected product in terms of how it interacts, how our users interact with the product. So that's what it looks like. This is a speaker. It has 2 side boomers which deliver bass, and what you can see on the front is basically a medium and a tweeter. So it's an all-integrated connected speaker. We have 3 models, same thing. We only change the output power, which we measure in dB SPL for sound pressure level. It has Wi-Fi, PLC, and Ethernet connectivity, and it uses a custom Linux distribution we made using Buildroot. The Qt for device creation offering did not exist when we started this project. So in many aspects, it was a real challenge. It was a challenge in acoustics. So our goal was to make the same sound as a speaker 20 times bigger in terms of volume, but also in terms of price. We had a very specific idea of how much sound we wanted to deliver in such a small enclosure. It was also a challenge in electronics. It was feat of engineering, we managed to reduce the size of our class A amplification, so the A amplifier I was talking about. We reduced it from roughly 600 square millimeters to just 1 square centimeter by developing our own ASIC. And it was also a very ambitious software project. So as I said, Devialet was not a software company. When we started, there were only 2 engineers in the company working on software, including 1 intern. So basically, it was really step 0. The product definition required many different operating modes. So the speaker could be used standalone or in a configuration of a stereo pair or in a multi-room system where you could have up to 24 in your house. So all those created additional constraints on the software team. One big issue was that the hardware did not exist when we started working on the software. So we had no way to develop directly on the target, or more to test on the target until really late in the project. And one other big thing that we sort of overlooked at the beginning is that configuring and operating wireless apparatus is really something that's not easy for consumers to do. So we started with an analysis of what we could do. And basically, we first looked at standards. So we looked especially at UPnP DLNA stacks, and also something's coming up which is called AVB for audio-video bridging. The main problem we had is that none of those technologies fit our product definition. So we wanted to do a multi-channel, single speaker sort of a thing where each speaker is basically a mono speaker, and you can have one playing left, one playing right, and it's not really common in the field. Like you can have AV amplifiers with DLNA integrated, but they integrate both channels. It's playing both left and both right. And because we have like dedicated and separated discrete speakers, we had synchronization problems you don't have with other technologies. Multi-room management is also something that does not exist as a standard, so we had to come up with something. And wireless operation, again, is not something that's fully standard in terms of how do you get your speakers to connect to a Wi-Fi network or to connect to your home network. So this created a product that was really different from what existed on the market, at least with open source technologies. Our competition already addressed many of those issues, but for us, we had to start from scratch. Another issue, as I said, was that complex and dynamic network configuration was a big topic. When you want to stream real-time audio across a Wi-Fi network, you have to deal with things like quality of service, and these are topics that the software team was not used to. So we had different strategies to address those problems. The first one was to create a companion to Phantom called Dialog. So Dialog is a custom router that we developed at Devialet. It has a lot of connectivity. It's designed to be connected to your home network via Ethernet. It's not a speaker, so you can basically put it anywhere in your house next to wherever your internet connection is incoming in your house. It has 3 Wi-Fi interfaces, and it's also a PLC adapter. And because we wanted to give it a bit more value, we also added an optical input so that our users could plug in anything basically in their system. We also had to create an app we call Spark, which is the companion application to our product. So it deals with this critical phase that is the setup, but also provides control for the system when it's fully operational. So we had to target multiple operating systems, so iOS, Android, macOS, and Windows. And you can see how Qt fits this picture. So just a quick look to give you a quick sight of what the application looks like. It has 3 panes, one for managing sources on the left, what we call the play queue, which is basically your current playlist in the middle. And on the right, you have speakers and volume and room management. So this is the same application on desktop. You can see that we've been able to reuse some components. So given the problem we had at hand, we had to come up with an architecture. So there was a lot of hype for microservices in big web infrastructures, and it turns out that it can fit pretty well smaller systems, including a home entertainment system. So our model is based on microservices. Each feature of the system is basically a single lightweight, single-threaded daemon running on different parts of the system. Given that there's no single point of failure, which was an important thing for us, if you lose connectivity with one of the speakers, you don't want the whole system to go down. And it's a very flexible design. It turned out to be very flexible because we've been able to integrate new sources and new technologies. We didn't have Bluetooth at the beginning. We integrated Bluetooth using the fact, simplified by the fact we had a microservices architecture. So the key components for this architecture were to manage host discovery, service registry, so a place where every service can register to let the other services know or other applications know that it's running on some endpoint on the network, and an RPC framework. So we name those components Discovery, What's Up, and Call Me Maybe. We name all our components after songs, so that's something we do. So how Qt helped us build this product? So Qt promise is, or has been for a while, code once and deploy everywhere. So Qt, to most, is a cross-platform application framework. It was really the best, if not the only candidate we could use to address all the platforms we had, coming from embedded Linux for the product themselves, or iOS, Android, macOS, and Windows. And for many people in their mind, Qt is really a GUI application framework, but it's really not. You can use it for making really hidden processes deep inside products. It doesn't have to have a UI. It's really well suited for writing daemons as well. What's really cool about Qt is that it's open source, the development is really active on the product, and it has a very clear roadmap. And I'll explain that a bit later. And the commercial licensing was also really important for us because we target iOS specifically, which requires static linking, and LGPL doesn't cut the bill for that type of applications. So Qt also allowed us to have a very bizarre sort of development cycle where almost more than 90% of the development of the product was made on a Mac. A lot of code, thanks to Qt, is completely agnostic of the platform it's running on. So we've been able to write thin hardware abstraction layer libraries that we used and that we made placeholders for on the Mac, for example. And we could develop the whole system, the whole stack, without even having the hardware in the beginning. It also allowed us to have very fast iterations in the way we develop the software. When you have to work with the targets, you have to make sure that the target is here up and running. You have to build, deploy, run tests. And when you work directly on your machine, you benefit from all the tooling that exists for this machine. So on the Mac, you have visual debuggers, you have crash reports with stack traces automatically, which allowed us to really work on the fundamentals of the system without even touching the target hardware, which is really, really cool. So Qt Core and Qt Network allowed us start to be developed in parallel to hardware. In our company, software was really new, as I said. So they were really good at managing their hardware planning, like even the development of an ASIC, which was something completely new and which is really long-term. It takes almost years to do. They're able to manage that from a management standpoint. But the fact that we use Qt and that we were able to make all the software in parallel to the hardware, and all we had to do at the very end was to port our stack to the specific hardware, has been very beneficial for the software team, which we didn't have to be compressed at the very end of the project where we had to do everything with no time. It allowed us to develop and test the whole stack on desktop before porting to target. Porting was made really easily because Qt has all the right abstractions with QPA and the fact that its default event loop on Linux is glib based and stuff like that. It really eased the port for us. And it forced us to design the whole system in terms of simple and reusable components across all platforms. So basically, most of the code that we wrote runs in the product, in the applications. We have a very unified toolbox that we can deploy in the different applications we have. And I didn't go in length on the UI because I didn't really work on that, but QML allowed a single developer to address all 4 platforms. And this is also really a really neat feature of Qt, that you can target all those platforms with a single code base. So we reused some components across the platforms. We were able to use the exact same business logic across all applications, whether iOS, Android, or Windows, or whatever. And we made a bet on QML, because when we started, QML was not available on iOS. And we said, Qt has a clear roadmap. Within the time frame we aim for releasing this product, the Qt project said, we will have iOS support by that time. So we were really confident in the fact that when we would launch the product, the feature would be there, and obviously it was there. So these are all very neat features of Qt. So in this section, I want to talk about some of the, it's not really best practices, but some of the stuff that allowed us to move fast and to avoid some pitfalls that we could have encountered with just basic use of the tool. So firstly, we did not use QMake. We went straight for CMake. In CMake, cross-compilation is really a core concept. He has definitions for toolchain files. So porting to a new platform for builds, it's really just about writing a single file in which you say, this is a compiler, this is the default platform flags, this is a linker and everything. So it's really more advanced in that regard. It's also very useful for managing cross-platform, not builds, but all the things you have to do around building, like creating folders, moving files around, installing stuff. CMake is really good at that. It's also allowed us to avoid a lot of boilerplate. When you have to create a library, you have to, these are the public headers, these are all this stuff you can wrap into nice macros and functions. So CMake is pretty good for that. And since Qt 5, it's really a first-class citizen in the Qt ecosystem, because Qt now provides its own configuration files for Qt. So basically, you tell CMake, this is a path where you should look for Qt configuration stuff, and CMake finds it, and just it alleviates a lot of pain. Another thing is, because we do cross-platform development, one of the big things that you can do on average is use as many different compilers as you can, because different compilers have different expectations regarding your code and produce different warnings and errors. It's really useful to confront your code as soon as possible to a variety of compilers and get the best out of it. Don't be afraid to enable all warnings and even go pedantic. This saved us from some issues. So for the story, we released the product with a major bug, which was basically a non-initialized Boolean value, which basically said whether the product was up to date or not, whether it required an update or not. You can imagine the problem when the product, because it's not properly initialized, says, I don't need any updates, I won't update ever. We were stuck with some products which could not update. We had to find workarounds and stuff. So enabling warnings and taking care of warnings is a very good way to avoid this type of things, because once you enable all warnings, an uninitialized Boolean value is something that you're going to be told about. And you should really aim for 100% warning-free builds with all that enabled, at least for your code. You can use libraries which are not as thorough in terms of managing warnings and errors. That's fine. But for your code, you should go aim for that. Another thing is you should really keep Qt up to date as much as possible. Every release has bug fixes and new features that solve a lot of problems. Globally, it turns out that using the more recent versions of Qt and the evolution of the APIs allowed us to reduce the code size and produce ultimately better code. And the risk associated with updating to us is really low because our testing compared to the Qt framework testing is just nothing we can compare. So we're much safer updating Qt than touching any other line of code in our code base. And then use modern compilers. C++11 is really a must now. Qt 5.7 made it a clean requirement to build to build this version, and the support for older compilers were removed. So in terms of development, we really benefited from developing first on the desktop, making sure that everything worked fine on that platform first, and then deploying to the target. It's faster iterations. You really win a lot of time without having to, I don't know, just you have a crash on target, you have to SCPs a dump back to your desktop to get the stack trace and stuff like that. You lose a lot of time working like that. If you can work on the desktop first, use the tools on the desktop, you win a lot of time. And by doing that, you make sure that your code is really portable and that you'll be able to leverage it in your desktop application, mobile applications. Write single-threaded code. I can't stress that enough. Multi-threading has many pitfalls. A lot of developers are confident enough and skilled enough to do it. We have a lot of junior developers, and I can guarantee that it leads to problems. So as much as possible, most of the things we need to do can be single-threaded. Only very specific use case in our system require multi-threading, and this is just real-time audio streaming with GStreamer. That's okay, you need maybe multi-threading with real-time thread and stuff like that. But most of the case, for pure business logic, you don't need it. Use UTF-8 for all 8-byte textual data. That's something that's maybe not obvious. On desktop platforms specifically, we're in France. Windows has really weird 8-bit encodings, so just use UTF-8, you'll be safe. And again, use C++11 in your development. It turns out that lambdas, just the feature lambdas of C++11 should be enough to convince you. When you don't have to write a specific slot to handle a signal or whatever, you can just inline that with a lambda. It's really, really useful. Finally, some of the specifics of embedded development. We recently made a pass on our code base to remove all unnecessary QObject macros. It's really not necessary. It used to be because we needed to declare slots, but now with the new C++11 connect syntax, which use pointer to member functions, you don't need to do that at all. It really reduces the final binary size, which is important for embedded. So we have a lot of room, space to hold code on the devices, but we need to take into account that updates have to be downloaded. And when you download stuff, everybody does not have a fiber connection, so it can be a real pain for our users. So making binary smaller is usually a good thing. And it also reduces the time for compiling your code, which still accelerates your development cycle. What you can do is use your own macro instead. That's what we're planning to do. So mock, since Qt 5, now does full template expansion, which it did not do before. So basically, you can define a macro, which you can use for debugging purposes or tooling purposes when you need introspection, when you need to be able to figure out what object you're handling. But that in production, in release builds, can be defined to nothing. So that's a strategy we're planning to put in place. Thank you all for coming. That's it. If you have any questions, you're more than welcome.
Thank you, Romuald. Anyone have any questions? Actually, I kind of had one. So just from a physics standpoint, you're trying to take, I think it was 1/6 the speaker elements.
20 times smaller, yeah.
20 times, sorry.
Yeah.
How do you actually manage the physics of that? Like, isn't a lot of what a speaker does moving air, and how does that get solved?
So it has to do with that, and it's basically we have a technology where we can model speakers. So we do some measurements on speakers, and we know exactly how they respond to an input signal. So we're able to basically, with DSP processing, to change the signal so that it really matches what the speaker is capable of doing and pushing air out on the
And
outside.
basically increases the efficiency.
Yes, and thanks to that, we have very tight control of how the speaker moves, and we're able also with acoustics and stuff like that to recreate this volume of sound.
Cool. Any other questions for Romuald?